Welcome to the fifth lecture on C-star algebras, titled Ideals and Quotients of C-star algebras. The kernel of a star morphism is always the closed and star-closed ideal, and in particular it's a C-star subalgebra. On the other hand, in the theory of Banach algebras, the appropriate notion of an ideal is a closed ideal. In particular, if A is a Banach algebra, and I is a closed ideal in A, then the quotient of A by I is again a Banach algebra for the quotient norm. Now there is an apparent problem. We seem to have two notions of ideals. Closed ideals, as in the theory of Banach algebras, and closed star ideals, which arise naturally as a kernel of our star morphisms. We see in this lecture that in fact they are the same notion. The consequence of this observation is that the quotient of a C-star algebra by a closed ideal is a C-star algebra, and thus every closed ideal in a C-star algebra is the kernel of a star representation. So we begin this lecture with a theorem upon which all the proofs of this lecture will be based, and which is essentially a local version of the proof of existence of approximate identities. Let I be a closed ideal in a unital C-star algebra. If X is an element of our ideal, then we can find a sequence En of self-adjoint elements in the ideal, whose spectrum is contained in the closed interval 0, 1, and such that the limit as n goes to infinity of the norm of x times En minus x is 0. Similarly, the limit as n goes to infinity of the norm of En times x minus x also 0. Let's prove this result. Let x be an element of our ideal I. Now let's first assume that x is self-adjoint. For any natural number n, I define a continuous function from R to the closed interval 0, 1 by setting for any t that fn of t is nt divided by 1 plus nt squared. Since x is a self-adjoint element, its spectrum is a subset of the real line, and therefore fn restricts to a continuous function on the spectrum of x. So by the functional calculus, I can define the element En as being fn of x for all natural number n. And using the general theory of the Gelfand transform, we can deduce that En is a self-adjoint element whose spectrum is a subset of the closed interval 0, 1. Somewhat less immediately obvious is the fact that since fn at 0 is 0, it is possible to approximate the function fn uniformly on the compact spectrum of x by polynomials which must have 0 constant term. What it means is that n, written as fn of x, is the limit in the norm of the C-star algebra of expressions that are polynomials in x, but not the unit of the C-star algebra. And a polynomial in x without the unit is of course an element of the ideal, since the ideal is in particular an algebra. And since the ideal is closed, it contains any limit of such polynomial, so it actually contains the element En. Once we've made this observation, it's then easy to calculate that the norm of x times En minus x using the Gelfand transform, and in particular its isometric property, is a supremum for t ranging over the spectrum of x of the absolute value of t fn of t minus t, which we can calculate as a supremum for t ranging the spectrum of x of 1 over 1 plus nt squared. And of course, the function 1 over 1 plus nt squared will converge to 0 uniformly on the spectrum of x. Therefore, we have shown that indeed the limit as n goes to infinity of the norm of x times En minus x is equal to 0. Then En times x equals x times En, because here in this case En is in fact commuting with the element x. So we have shown our theorem for the special case of self-adjoint elements in our ideal. It's now reasonably easy to get the result for an arbitrary element in an ideal. So let x be an arbitrary element in our ideal. Well, using the ideal property, we can conclude that x star times x is also in the ideal. Now, as before, we can find a sequence En of self-adjoint element in our ideal, whose spectrum is contained in the closed interval 0, 1, such that the limit as n goes to infinity of the norm of En times x star x minus x star x equal to the limit as n goes to infinity of the norm of x star x times en minus x star x, and both are equal to 0. This is, of course, because x star x is a self-adjoint element in our ideal. Now we are going to use the C star identity to conclude the desired result. So for any natural number n, the norm of x times en minus x equals to the norm of x times en minus the unit. Then if we apply the C star identity to this, we get that this norm equals the square root of the norm of en minus 1 times x star x times en minus 1. Remember that en is a self-adjoint element. Now, using the fact that the norm of a C star algebra is an algebra norm, we can conclude that this quantity is less or equal than the square root of the norm of en minus the unit times the square root of the norm of x star x times en minus x star x. The second factor goes to 0 by construction of en. And for the first factor, remember that en has a spectrum contained in the closed interval 0, 1 and is a self-adjoint element. So using the Gelfand transform, it's easy to actually show that the norm of en minus a unit is actually less or equal than 1. So we have shown that the limit as n goes to infinity of the norm of x times en minus x is indeed 0. And the other limit is proved exactly in the same manner. So our theorem is shown. Now in this particular theorem, I point out that the sequence en that is given by the theorem depends on the element x. But we will see later on in this lecture that there is a way to talk about approximate units of ideals without having this restriction. We will find a way to make an approximate unit that is valid for all the elements at once, to the cost maybe of extra technicalities. However, this result is sufficient for all the proofs in this lecture, and in fact, it is really the key step in establishing the existence of a global approximate unit. Now let's prove the main result of this lecture, that is, closed ideals of C star algebras are themselves C star algebras. Let I be a closed ideal of a unital C star algebra. If X is an element of my ideal, then the adjoint of X is also an element of the ideal. Since a closed ideal of a Banach algebras is already a Banach algebra, this theorem indeed implies that closed ideal of unital C star algebras are in fact themselves C star algebras. Let's prove our result. Let X be an element of our ideal I. By the previous work, there exists a sequence En of self-adjoint element of our ideals, which have spectrum contained in the closed interval 0, 1, and such that the limit as n goes to infinity of the norm of x times En minus x is equal to 0. Now, since I is an ideal and En is by construction an element of I, then En times the adjoint of x is also an element of our ideal I. But on the other hand, the norm of En times x star minus x star, well, that's equal to the norm of x times En minus x because En is self-adjoint, the star operation is an isometry, and the star operation is intermultiplicative and conjugate linear. Therefore, again by construction, the limit as n goes to infinity of the norm of En times x star minus x star is 0. But that means that x star is the limit of elements in the closed ideal I, and therefore x star is itself in the ideal I as desired. Therefore, there is no need to introduce the notion of a closed star ideal. The usual notion of an ideal in Banach algebras, that is, closed ideals of Banach algebras, is in fact perfectly appropriate in the realm of C star algebras because these closed ideals are automatically closed for the star operation and in fact are automatically C star algebras. We are now able to discuss quotients of C star algebras. If A is a unital C star algebra and I is a closed ideal of A, then the quotient of A by I is again a unital C star algebra, and the canonical surjection is a star morphism. To prove this result, we will begin with a lemma which extends on the work we started this lecture with. It gives me an expression for the quotient norm in terms of certain self-adjoint element of the ideal. So if X is in our C star algebra, and I sub 1 is a collection of self-adjoint element Y in the ideal whose spectrum is a subset of the closed interval 0, 1, then the norm of the equivalence class of X is the infimum over all the Y's in I1 of the norm of x plus x times y. So let's prove our result. Fix x in the C-star algebra, and we'd like to calculate the norm of the equivalence class of x as stated in the lemma. First, observe that since I is an ideal, if y is an element of the ideal, then x times y is an element of the ideal. Therefore, the norm of the equivalence class of x is less or equal than the norm of x plus x times y, by definition of the quotient norm. Thus, we already have shown that the norm of the equivalence class of x is less or equal than the infimum for y ranging over the set I1 of the norm of x plus x times y. To prove the converse inequality, let epsilon be strictly positive. By definition again of the quotient norm, there exists y in the ideal I, so that the norm of x plus y is less or equal than the norm of the equivalence class of x plus epsilon. Then, using the first result we established in this lecture, there exists an element e in I1, such that the norm of y minus y times e is strictly less than epsilon as well. From this, we deduce the following. The norm of the equivalence class of x is less or equal than the norm of x minus x times e, since minus x times e is indeed an element of the ideal. This in turn is less or equal than the norm of x plus y times 1 minus e plus the norm of y minus ye, simply using the triangle inequality and some algebra. Now the norm of y minus ye by construction is strictly less than epsilon. On the other hand, the norm of x plus y times 1 minus e is less or equal than the norm of x plus y times the norm of y minus e. And again, owing to the fact that e is a self-adjoint element whose spectrum is contained in the closed interval 0, 1, using the functional calculus, we know that the norm of 1 minus e is actually less or equal than 1. Consequently, we have shown that the norm of x minus xe is less or equal than 2 epsilon plus the norm of the equivalence class of x. And from this, you see we can deduce that the infimum for y ranging over the set I1 of the norm of x plus x times y, well, that's less or equal than the norm of x minus x times e, because minus e is an element of I1, as easily checked, which we've just shown is less or equal than 2 epsilon plus the norm of the equivalence class of x. And since epsilon is arbitrary, we get the converse inequality, and our lemma is proven to be true. So let's use our lemma now to prove our theorem. First of all, you want to define an adjoint on what is already a Banach algebra, namely the quotient of our C-star algebra by the ideal. And the obvious idea is that if you take an element x of the C-star algebra, the adjoint of the equivalence class of x should be simply the equivalence class of the adjoint of x. And this does work precisely because ideals are self-adjoint. That is, if it is true that the equivalence class of x equals the equivalence class of y, that is, then x minus y must be an element of I, but that also implies that the adjoint of x minus y is an element of I, and therefore the equivalence class of the adjoint of x is the equivalence class of the adjoint of y. So this notion of an adjoint is well defined. And you may immediately notice that the canonical surjection becomes by construction a star morphism for this adjoint operation. It is easy to check that this adjoint operation has all the desired properties. It is conjugate linear, anti-multiplicative, isometric, and involutive. In fact, precisely because the canonical surjection is a star morphism, all the properties except for isometry are immediate consequence of the same properties for the adjoint operation on the C-star algebra. As an example, now I'm going to show to you that indeed this new adjoint operation on the Banach algebra A quotient by I is indeed an isometry. And I'm going to simply use the fact that my ideal I, being a closed ideal of a C-star algebra, is closed under the adjoint operation, and that the adjoint operation is an isometry at the level of the C-star algebra. If you pick x an element of the C-star algebra, the norm of the adjoint of the equivalence class of x is by definition the infimum for all y ranging over the ideal I of the norm of x star plus y. Then you can rewrite x star plus y as the adjoint of x plus y star, and thus this norm equals to the infimum over all y in your ideal of the norm of the adjoint of x plus y star. But now the adjoint on the C-star algebra being an involution, it's a bijection, and it easily is checked to map the ideal to the ideal again, since the ideal is closed under involution. So this in turn tells me that the norm of the adjoint of the equivalence class of x is the infimum for y ranging over my ideal of the norm of the adjoint of x plus y, and the adjoint being an isometry, this in turn again equals the infimum over y ranging over the ideal of the norm of x plus y, which by definition is the norm of the equivalence class of x. So we have defined an operation on the quotient that has all the necessary properties of the adjoint except for the C star identity. And note, of course, that the norm on the quotient a by I is an algebra norm. If x is an element of the C star algebra, then the norm of the equivalence class of x star x is less or equal than the product of the norm of the equivalence class of x by the norm of the equivalence class of x star. And we've just seen that the adjoint operation is an isometry on the quotient, so this, in fact, this product equals to the square of the norm of the equivalence class of x. This is a general observation about isometric involution, of course, so what we really must show in order to conclude our theorem is that for that x, the square of the norm of the equivalence class of x is less or equal than the norm of the equivalence class of x star x, and then we would have the desired C star identity. So I'm going to use the same notation as before. Let I1 be this subset of my ideal consisting of the self-adjoint element of the ideal whose spectrum is contained in the closed interval 0, 1. We know that the square of the norm of the equivalence class of x equals to the infimum over all y in this I1 set of the norm of x minus x times y squared. But then we can use the C star identity in the C star algebra A, where this calculation takes place. So this equals to the infimum over all the y's in I1 of the norm of 1 minus y, x star x, 1 minus y, which is simply applying the C star identity to x times 1 minus y. But this, of course, is less or equal than the infimum for y ranging over all of I1 of the norm of x star x times 1 minus y, because again, the norm of 1 minus y times x star x times 1 minus y is less or equal, using the algebra norm property, to the norm of 1 minus y times the norm of x star x times 1 minus y. And the norm of 1 minus y is less or equal than 1 by using the functional calculus on the self-adjoint element y, whose spectrum is a subset of interval 0, 1. And you recognize, again, applying our previous lemma, that the infimum for y ranging over I1 of the norm of x star x times 1 minus y is in fact the quotient norm of x star x plus I, that is the norm of the equivalence class of x star x. And thus our proof is complete. So we were able to show that indeed, in the subcategory of C star algebras within the category of Banach algebras, ideals and quotients are actually again C star algebras, without the need to introduce any new notion to get this apparently stronger property. It just comes naturally from the structure of a C star algebra. So let's conclude this lecture with a nice result. If A is a unital C star algebra, then a subset I of A is a closed ideal of A if and only if it is a kernel of some star representation of A. Indeed, first note that the kernel of a star representation is of course a closed ideal. On the other hand, if I is a closed ideal, then we've just seen that the quotient of A by I is a C star algebra, a unital C star algebra. Thus, by the Gelfand-Naimark theorem, there exists an injective unital star morphism from that quotient to some C star algebra of bounded operators on a Hilbert space. And by composing this injective unital star morphism with the canonical surjection, which is a star morphism and unital as well, we get a star representation of the original C star algebra on the same Hilbert space, whose kernel is I, owing to the injectivity of the Gelfand-Naimark star morphism. So this is interesting because you can use this association to try and topologize the star representations a little bit. It is indeed possible to put topologies on ideals, and in doing so, we can put topologies on the representations. Now, those topologies will certainly not be Hausdorff. At the bare minimum, obviously unitarily equivalent representations would have the same kernel, but in fact, more generally speaking, there are C star algebras like the quantum tori, which can be simple and yet have infinitely many non-equivalent representations. So in that case, the topology induced on the representation using the ideal structure would be trivial, since there is no proper ideals, and yet at the same time we have many representations. So that's an extreme example of not having a Hausdorff topology on the representation from the ideals, but you can get some interesting traction nonetheless with this sort of ideas. Another question you can ask is, what is special about, say, the ideal that's a kernel of an irreducible representation? Well, those are primitive ideals. Or what about notions of kernel of other interesting representations? So another way to look at this once more is that to some degree, studying star representation of C-star algebras seem to be a more promising avenue than just studying the ideal structure of C-star algebras. Even fairly simple C-star algebras in the naive sense of simple are indeed simple in the technical sense. The algebra of 2x2 matrices is simple. It has no non-trivial ideal. So you can't say a whole lot about the ideal structure for many C-star algebras, algebras of compact operators, simple quantum tori, etc. But you can say a lot about their star representation. So this theorem tells us that basically one way to look at ideal theory is just as a chapter of the theory of star representation.